So we're going to be talking about functions and graphs, continuation from like last class. So we're going to draw more graphs. We're going to graph transformations and look at even and odd functions. So this is where we left off. The vertical line test helps us to determine those that are indeed graphs of functions. So what is this vertical line test? Let's underline it. So a set of points in the coordinate plane in the graph of some function, if and only if each vertical line intersects that set at most one point. So we can kind of draw an example of this. Whoops, imagine that's a straight line. Now suppose you had a function like this. Or it's not a function, a line like this. Is it a function? Just kind of gave the hint, right? Why is that? Because the vertical line test says if you draw a vertical line and it intersects more than once, so here it intersects 3 times, then it's not a function. So let's write that down. So back to, so this pink line means, so this curve is not the graph of a function. By the vertical line test. Now, let's draw a different curve. Black. Say it starts here, goes down, goes up again here. Is this a function? The black curve? Yes, because if we draw a vertical line, it only intersects once. So the black here. So this curve is a graph of a function. By that vertical line test. And you can see like this red line back to the pink graph or curve. This red line, it intersects it here and here and here. So we can make a little note saying like this vertical line, just so you remember, intersects the graph in more than one point. So this implies the red, so the pink curve is not the graph of a function by that vertical line test. That's where I was actually going to draw the picture. Thought I was missing that slide. Okay. Anyways, we can just move that there. So function transformation and graphs. It's a good idea to know like the graphs of some important functions by heart. So some functions are very important. This is useful because you can apply some operations on functions to transform a function into a new one. So if you know the graph of a function, using these transformations, you can easily figure out the graph of infinitely many new functions, infinitely, but not all of them, by using like, but by knowing the basic ones first. So consider this function, x squared defined on -1 to 1. What does this look like? So you can, how to graph it too, for the first time. So it goes from -1 to 1. Here. And we can do a table of values for the function of f of x equals x squared. So it's gonna, you can start plotting. So the domain goes from -1 to 1. So -1, we can do intervals, -0.5, 0, let's say 0.5, 1. Could do some others like 0.4, 0.8, other ones too, if you wanted between here. Now you can plot this. So you take the x value, that input, you put it into the function. So it'd be like -1 squared, which is just 1, -0.5 squared, which is 0.25, 0 squared is 0, 0.5 squared is again 0.25. 1 squared is 1. And here are some extra points, but I think you get the idea. So you can just make a table of values and then you can plot them. So this is your ordered pair, 0, 0. So that's your first point. Label maybe a few more points here. So at -1, we have 1. At -0.5, we have 0.25. So it's about here. At 0, we have 0. At 0.5, we have 0.25. At 1, we have 1. At 0.4, we have about a point, about 1.6, which is about here. And at 0.8, we have a point about here. So then you can kind of connect the curves. This is 0.25. Or connect the dots and you get a curve. You notice something about this graph. Sorry, I drew it nicely. It's symmetric. Around the y-axis. So this is one of the most important graphs that you'll probably see, this x squared graph. it tends to show up a lot. Now, there are three types of vertical operations that we want to examine. So this is about changing the shape. The first one is shifting a graph up or down. Suppose f is a function and a is greater than 0. So we define g and h by g is equal to the function plus a, and h is equal to the function minus a. So then the graph basically of g is obtained by shifting the graph, either moves up or down a units respectively, or down a units. So let's look at an example. Suppose you have, again, x squared and a is 2. Draw the graphs of f, g, and h on the domain -2 to 2. So again, we kind of draw that function, but this time it goes from -2 to 2. So we know, let's say -2 is here, -1, 0, 1, 2. So 2 squared is 4. So 1. So we know it's going to, the first one's going to go up. So we can first begin by just drawing the regular function, f, which is x squared. So we know the points here and here. 1, about here, and -1 was here. So you can connect those dots like we previously did. And this blue one is going to be right over here, x squared. Now we want to add a, so for that function, let's say g of x is going to be f of x plus a, meaning this is going to be x squared plus 2. So what happens to that graph when we add 2? Yes? Right, so there's a shift up of 2 units. So it just basically begins here, 2 units, and it's the same kind of graph, just gets shifted up. So this would be the graph obtained by shifting the graph of f of x up by 2 units. What about the next one? Let's change the color to black. H of x is going to be f of x minus a, which is going to be x squared minus 2. What are we going to do? Yeah, so we're going to just shift this graph, this blue graph, down 2 units. So we just shift it down. That's it. So this graph is obtained by shifting a graph of f of x down, essentially. Keyword. This one's up by two units. Yes?
It says 8 equals 2, so why are we graphing down?
Pardon?
Why are we doing both up and down? Why are we doing both?
Oh, it says to draw the graphs of f, g, and h.
Oh, H is negative,
H was back here. Yeah, h was f of x minus a.
okay. Oh, okay.
Yeah, probably just, it's over here. Yes?
I see that the graph goes up and down. Was there like a formula that makes it go left and right?
Yep, we're getting there. We're going to the left and right. We're doing the same thing. It's repetitious today. Same idea. Now we're going to stretching a graph vertically. Suppose f is a function where c is greater than 0. And we can define this function g by f of x times c. Then the graph of g is obtained by vertically stretching the graph by this factor of c. If c is between 0 and 1, then the stretching by a factor c means the compressing, shrinking of the graph. So we're just going to shrink it. So we're going to draw the same graph. Now, shrinking it and compressing. So again, we draw our f of x, draw the graphs f, g, and h. And you see the factor here is 3 and 1 over 3. So what happens on the domain -2 to 2? Goes to 4. Sorry, it's hard to draw. So how do we do this x squared times 3? Pardon? Right, so basically this part here, this 3 is our new c, and we can think of it that way. So we could say when x equals 1, we actually get 3, right? So 1 squared times 3. Here it's going to be 2 squared, so 4 times 3. So it's going to be way up there. Can't draw it. Da, da, da. So you see that it kind of like compresses it. -1 squared is 1, 1 times 3, 0. So the idea is just to be able to sometimes have a visualization of this. So this graph is g of x equal to 3 times f of x. And then the other one, black, kind of the same ideas. So it's just like 1 squared is 1, 1 times 1 over 3, or to kind of label this. It's going to be down here. 2 squared is 4, 4 times 3, it's going to be 4 over 3, so it's about here. And then it's symmetric, so it's the same side on the other side. we can kind of draw them, these parabolas, a little bit nicer. They're called parabolas. This is h of x equals 1/3 f of x. Now we can also flip. Flipping a graph along the horizontal axis. Suppose f is a function and define g as g of x equals negative f of x. And the graph of g is just obtained by flipping, reflecting this graph, ff, across the horizontal axis. And it's basically a vertical operator on this. So let's see an example. Again, it's on -2 to 2. It's not exactly drawn to scale because I'm putting a 4 here. Actually, the 4 should go up there. Erase this. So it looks something like this. Now, this is where, like, sometimes if you're not sure what to do, a table of values comes in handy. So you could draw, just put it to the side from -2 to 2, the values of f of x and g of x. And g of x is just negative f of x. So like before, we got a -2 squared was 4. -1 squared was 1, 0 was 0. 1 squared was 1, and 2 squared was 4. So the negative of these values, this would be -4, -1, 0 again, -1, -4. So essentially, it's just going to be, again, that reflection in this axis. So -4 down here. And you plot it. So -2, -4, -1, -1, 0, -1, 1. So it just gets reflected. So this g of x equals -x squared, and it's just obtained by flipping the graph of f of x across the horizontal axis. You can see, like, it's almost like a reflection, right, in that axis. So now there's also, did everything. I guess I have some extra slides there if you were, sorry about that. So there's also 3 types of horizontal operations that we often use. Shifting a graph left or right, And this is a little bit different. So if you have a function and b is greater than 0, so you can define g and h the specific way, where x plus b is in the brackets of the function, and h is equal to f, where x minus b is in the brackets of the function. Then the graph of g is obtained by shifting the function left b units, and shifting the function of h is obtained by shifting the graph of f right units. And we'll look at a picture. So let's draw this one. It's a little bit more complex here, I find. It's been straightforward until this point. So we can do that table of values again. So -2, -1, 0, 1, 2, just choose obvious points. The function of f of x, again, we know this is for 1, 0, 1, and 4. And we can plot it. And 1, 2, 4, 1, 1, and connect. So my graph is not perfect. You will draw a better graph with pen and paper than I can standing on an angle like this. Now, what happens when we shift it? So let's see. So g of x is this function here above. So when we put in, let's say, -2 into this, -2 plus 2 is 0. So 0 into this function is 0. So this becomes 0 squared equals 0. So it's kind of a little bit counterintuitive. So at -2, you get 0 here. Let's do the next one. At -1, you have -1 plus 2. So that's 1. And then you plug it in. So that's 1 squared, which equals 1. So at -1, you get 1. At the next point, at let's say 0, 0 plus 2 is 2. 2 squared is 4. And so on. So you get this graph. And we remember that it's symmetric. So it's kind of like flatter here. If you take like smaller values and then it goes up like that. What about h of x? So h of x has a negative here. So we start with -2, subtract 2. Actually, it's easier if we start the opposite way. So let's say 2 subtract 2 is 0. So 0 plugged into the formula is 0 squared is 0. So at 2, we have 0. So you see it shifts the opposite way of what you might see in the formula, in the function. At 1, you have 1 minus 2 is -1 squared, so you get 1. And then you can do the rest. I'll just write them out for you. So at 1, you get 1. At 0, 4, so on. It did just say the domain from -2 to 2, so I'm just correcting it, like little dashes. Because you only have to do it from -2 to 2, but that's the idea. Okay, so stretching a graph horizontally. Suppose f is a function and c is greater than 0. Define this function g by f, and then c is multiplied by x within the argument of the function. So then the graph of g is obtained by horizontally stretching the graph of f by this factor of 1 over c. Note that if c is greater than 1, then 1 over c is less than 1. So this case is just the same thing, kind of, but stretching the graph by a factor of 1 over c, then shrinks it. The important point to note of all this is f of cx does not equal c times f of x. They're not the same thing. They are not tomato, tomato. They're apple and orange. So be careful. So let's see what, because now c is inside of the function before c was outside of the function. So it's a little bit different. And we're stretching either the function horizontally. So again, we're going to draw our favorite function. And again, I have to redo. Not much better. So it's from -2 to 2. So 1, 2, 4, 1, and negative. It's a little flatter near the 0, and then it goes up kind of exponentially. Now you could do like a table of values, or you can start like just plugging in some points. So I'm going to just write it out here. So f of 0, or h, let's do the h one here. H of x equals 1 over 3 times x. So at h of 0, this is kind of a different way of doing it, but same thing as table of values. You have 1 over 3 times 0, which is just f of 0, so you have 0. So it begins at 0. H of 1 is going to be just f, because it's equal to f, over 1 over 3 times the 1, which is f of just 1 over 3. And then f is x squared, so you plug in 1 over 3 into the function, get 1 over 3 squared, and get 1 over 9. So it's the same table of values, I'm just writing it this way. H of -1, you see will be the same thing, kind of 1 over 9 due to symmetry. H of 2 is going to be a little different. So it's the function 1 over 3, x equals 2, f of 2 over 3, plug it into x squared, and we get 4 over 9. And then the last one is the same due to symmetry. It's 4 over 9. So we can like plug like these values and you see, well, at 1, we get 1 over 9. So it's much flatter At 2, we get 4/9, which is, yeah, really flat. And then same thing on this side. So you mark your points. I'm just extending it so you see the idea, the symmetry. And then we can also do it off for g. G of x at 0 is obviously going to be f times 0, the same idea, times 3. Sorry, these should be flipped. Anyways, it's f of 0 equals 0. So again, it starts at 0. G of 1 is going to be f times 3 times 1. So we're going to get f of 3. This time, 3 plugged into x squared, we're going to get 9. G of -1 is also going to be 9 due to symmetry. G of 2 is going to be f times 3 times 2, which is f of 6. Plug in 6 squared equals 36. And then g of -2 is going to be 36. So you see it changes a little bit. So at 1, we have like 9 all the way up here. So it's hard to, so we didn't. So it really squishes in here. So you see the black, so they're the same except for like the black curve, black function. Just observe that it's the graph, that the graph of h of x is like is exactly like f of x, except for 3 times wider. And then the last, I think, point, we can flip a graph across the vertical axis this way. Suppose you have g, we can put a negative few here. So then the graph of g is just obtained by essentially flipping the graph across this vertical axis. So it's like multiplying basically each number in the domain of f by -1. So it's kind of like what we did before, because c was a number. Here it's a -1 and it just flips. So to draw, and I won't draw the whole graph, but like, okay, so from -2 to 1. So this is more interesting. So from -2 to -1, draw the graph. So it's the same graph. So it's something like here and here. This is 4, I believe. This is 1. And I should just make one point here. A point also is that f of -x is not equal to -f of x. They're not the same thing. So how to draw this? So we have this function. This is the function f of x equals x squared on this domain. And we have our domain is specific -2 to -1. You know, what is the range? Anyone? Of f of x? Yeah. So it goes from 1 to 4. because those are our y values. So essentially what we can do, and you can check this yourself, but I'll try to say it. It's a reflection along that vertical axis. So this point comes here, and this point comes here. So this is our new g of x, and it's equal to our f minus our x, which is our negative x squared. And again, we see our domain is going to be now going from 1 to 2. And our range, what is our range of our new function of our g of x? Yeah, it's 1 to 4. So what do you notice about the range? It's just basically the same, right? So the range of g of x is basically equal to f minus x is the same as the range of f of x. So they have like the same range. Now, the cool thing about these transformations, and you use this in algebra, is that you can actually combine all of these operations in many different ways, which allows us to form many new functions from a given function. So suppose you have like this particular function, x squared, again, our favorite function, with a domain from 0 to 1. Let's say we wanted to draw this type of function where we plug it in. So g of x is going to be negative 3x squared plus 5. So it's like a polynomial, which I'll explain this. So again, we can, it's only from 0 to 1. Or yeah, so 0 to 1. So it's like this, or for f of x, x squared. And then, so we can combine it like kind of like step by step. So the next process you could do is you can multiply it by 3. So if you multiply it by 3, let's call it g of 1 of x. It's going to be 3 times f of x. You're going to get something up here. Here. Going to run out of colors, but I'll try. Then g of 2, we apply that. So let's say it's negative 3 times f of x. That's that flip in that x axis. So it'll be down here. So then we flip it. Now we want to add 5 to it. So let's, then we add 5. So 1, 2, 3, 4, 5. So then we're up here. So we take the black one and we add 5 to it, and it goes down like this. So you just shift it, move it, step by step. And this is like the final one. So the domain, you notice, is 0 to 1. But the range here of this particular function of g. So the range goes from, what is the range here? Well, I'll tell you. It goes from 2 to 5. You see here it got shifted up 5 units. So it goes to 5. This is our 5. Down here, this would be our 2. And you can see 1, 2, 3, 4, 5. So you can count. Hope that makes sense. So whenever you're dealing with a combination of horizontal and vertical transformations, it's best to take care of what's inside of F first. Those are those horizontal transformations go first. Anything inside the function goes first. When applying transformations, you do basically the same order of the corresponding operations when evaluating the function. So you have to write it in an appropriate way. So what about something like this? X squared between -1 and 1. Draw the graph of this function. Now you can check your work. I'm going to leave this one as an exercise, but I'm going to try to explain it. And you can use, we know Desmos from high school, correct? You can search. So just search this online for the graphing calculator. But how to do this? So we can rewrite it this way. The first thing you would do is horizontal maybe shift. Of f of x minus 2. So this would be, you plug this in and you get x minus 2 squared. Then you want to do a stretch. So you shift it first. You do inside here. Let's change the color. Then you want to the horizontal stretch of this function by this half factor. So then you want to stretch it. So apply that. And next, you would want to do the vertical stretch. Of this 2 here in front. Sometimes you could combine them if it's kind of obvious. And then you want to flip it with the negative sign. So then you do that -2. So you can graph a lot of these functions, essentially. And then the last step is adding the 3. Adding this 3. So finally, the vertical shift. So it's similar to like kind of bedmas, like there's inside first, and then you go outwards, but this time with functions. So I'll leave this for you for an exercise to do, this question. So you do all these operations. So please do these operations. Is that a little messy? Okay, 251. Then we'll talk about even and odd functions. Next class. And composite. Remember, you have a quiz